This tutorial will show how the calculated gravity load deformations in a building can vary depending upon the analysis technique used. An accurate accounting of vertical displacements becomes very important in taller buildings where effects can be magnified. If these vertical displacements are not correctly estimated, not only can structural elements such as columns, beams, slabs, and walls be affected, but non-structural elements such as piping and mechanical ducts, partition walls, elevator cores, and the like may end up being subjected to deformations and loads they were not designed for. In this study, our simple model consists of a single 20-story tall concrete column that supports tributary slab areas at each floor. The column is a constant cross-section for the entire height, and the size of the supported slab is 24 feet by 24 feet in plan. As a review, displacements in the column are a function of PL over AE. P being load, L being length, A being the cross-sectional area, and E being the modulus of elasticity. Note that P increases as you go down the column, but that L increases as you go up the column. In this model, the denominator AE is constant. We are going to run 3 different types of vertical analysis on the model to see how deformations are affected. We are concerned only with dead load or self-weight and superimposed dead load, as we are interested in how the building deforms during construction and prior to occupancy. Of course, additional deflection will occur when live load is applied. However, we are primarily concerned with permanent long-term loads in this study. The 3 different analyses we will perform will be as follows. First, we will apply the vertical load only after the entire structure is complete. This is traditionally how engineers have analyzed structures. Second, we will use construction sequencing, whereby load is applied as each floor is constructed, story by story. The last analysis will also use construction sequencing, but will include time effects as well, such as creep and shrinkage. We start by reviewing our load patterns. We have a dead load pattern with self-weight, and a superimposed dead load pattern that is used to assign mechanical and other permanent loads. We have also defined a load combination that contains the 2 load patterns. If we check the load cases, which are the analysis cases, we see that again we have 2 cases, same as the patterns. We can now run the first of the analyses where the load is applied as if the entire structure is already built. Displaying the deformed shape for the load combination, we see that the deformation at the top is about 1.3 inches. If we plot the displacements at each floor, we see how the displacements increase at each floor with the maximum at the top. The largest inter-story displacements are at the bottom, where the slope is the flattest. Now we will set up the model for our second analysis where we use construction sequencing. In this analysis, the building is constructed 1 story at a time. For example, here the first column and floor have been placed. Due to the weight of the structure, the column deflects. The next step is what differentiates construction sequencing from the first analysis. Here, rather than say that the next concrete pour will go from story 1 to story 2, we say that it will go from the deflected position of the first column up to story 2, thus compensating for the prior column's deformation. Stage construction or construction sequencing is very easy in ETABS. We go to the Define menu and select the Auto Construction Sequence Case command. We are going to assume that the concrete for the columns and floors will be placed one story at a time, although we could set it to 2 stories or anything we would like. In addition to the dead load, we will also apply the superimposed dead load. Again, these 2 load patterns comprise our permanent loads. If we were doing design as well as analysis, we could check this box to use this as our dead load case. We are now ready to run this construction sequence load case. Displaying the deformed shape for this case, we can see how the building is constructed. On the elevation view with the deformed shape plotted, we see that the maximum deflection at the top is about 0.12 inches, quite a bit less than the first case, which was about 1.3 inches. If we plot the displacements at each floor, we get the following graph. Note the parabolic shape of this curve. The vertical displacement at the top of the building is nearly identical to the displacement in the bottom story. How can this be? Let's perform a simple calculation. Assuming that all of the floor loads are identical, the first story column has a load of 20 W and a length of 1 H. That is, it supports 20 stories of floors and has a length of 1 story. Because each column is poured such that it compensates for previous deflections, the top story column deflection will be equal to just its own deflection, and it has a load of 1 W and a length of 20 H. Thus, PL over AE for the first story is 20 W times 1 H over AE, and PL AE for the 20th story is 1 W times 20 H divided by AE. Thus, they have equal deformations as the plot shows. When we plot the 2 curves together, note that the first analysis case results in column displacements that are always equal to or greater than the construction sequence case. Now we will do the last analysis, whereby we will include creep and shrinkage time effects in a construction sequence case. Creep and shrinkage parameters are defined in the material properties. Selecting the concrete property, which we are to modify, we click on the Time-Dependent Properties button. Here we can select the time-dependent type, which we will leave at CEB FIP 90. The code parameters may be adjusted here if necessary. Make sure that both creep and shrinkage are checked. and we will use the full integration creep analysis. Creep is a time-dependent increase of strain due to sustained stress, while shrinkage results in a decrease of concrete volume over time. Both of these have the net result of increasing the vertical deflection of concrete structures. Clicking the Show Plot button graphs both the creep coefficient and the shrinkage strain. Note that the time range is for 10,000 days, and our analysis is only being done for a total of 100 days. So chances are significant shrinkage and creep will continue after the building is built. Creep and shrinkage are now defined. Next, we return to the load case definitions. We will select the auto sequence load case previously used and click the Add Copy of Case button. We will name the case Case 3. Scrolling down the list, note that we have a total of 20 stages, one for each story. This is where we modify the duration of each stage. And we will enter the 5 days needed to place each story. Next, we click the Stage Operations button and set the stage to Stage 1. We are going to change the age at add from 0 to 3 days. This gives the concrete some time to cure before carrying any load. This is typically when the forms would be stripped. We will do this for all of the stages. If we click on the Show Stage Tree button, we can see how the stages are sequenced. Next, we click the Modify Show button for the nonlinear parameters. This is where we will activate the creep and shrinkage behavior. Expanding the material nonlinearity parameters list, we will switch on the time-dependent material properties. We have now defined a stage construction case that includes creep and shrinkage time effects. Setting all of the load cases to do not run except for case 3. We will now run the analysis. This time, when we see the construction sequencing, note the additional deformation behavior due to the time effects. This time, the deformation at the top of the column is approximately 0.43 inches. And when we plot the deformations at each story, our plot looks like this. Even though the deformation at the top is not excessive, there is significant interstory displacements, and these displacements are what cause significant issues with mechanical and non-structural components. If we plot all three analyses, we can see the significant impact that creep and shrinkage can have in a stage construction analysis. Again, the flatter the slope, the greater the interstory displacement. It is important to make sure that structural and non-structural components are designed to accommodate these relative displacements. To emphasize this point, let's take a closer look at the displacements for the second story. We are going to compare the interstory deformations for analysis case 1 and analysis case 3. Remember that analysis case 1 is where the loads are applied after the building is built, and analysis case 3 includes creep and shrinkage with stage construction. For case 1, the displacement at the top of the second story is 0.24 inches, and the displacement at the top of the first story is 0.12 inches, resulting in a relative deformation in the story of 0.12 inches. In case 3, however, the displacements are much larger. At the top of story 2, the displacement is 0.77 inches, and the displacement at the top of the first story is 0.43 inches, resulting in a relative deformation in the story of 0.34 inches, nearly 3 times larger than the relative displacement obtained for analysis case 1. This study dealt with a single column, but in reality, this analysis would be done for the entire building. It is important to be aware of differential deformation between structural objects. That is, all columns might not be loaded the same. For example, the P in PL over AE may be different at different locations throughout the building, and walls are typically at a different stress level than the columns, all of which results in elements that deform at different rates. After analyzing our revised model with an added wall, if we look at the deformations due to load case 3, we see that the displacement at the column is still about 0.4 inches. But the displacement at the wall is only 0.04 inches, only a tenth as much. This is an example of the differential displacement that can occur. However, there is a way that ETABS can help mitigate these differential displacements. Let's return to the elevation of the first story column. What if rather than placing concrete up to the next floor, we place concrete a bit higher than the story elevation, so that when elastic deformation and the creep and shrinkage occur, the column will settle closer to the desired floor elevation, and this will help reduce differential displacements. Now let's see how to do this in ETABS. Remember that our original model had story heights of 12 feet. We can verify this by right-clicking on a column. The length is 12 feet exactly. After having run the initial analysis, which was our case 3, we can alter the model geometry in ETABS to account for the deformations by using the Analyze Modify Undeformed Geometry command. Using this command, we can set a target displacement. That is, we can revise the original or starting geometry of our joints by moving them up an amount equal to the downward displacements. We will use the last stage of case 3 for the target displacements. Clicking OK modifies the undeformed geometry of the model. Switching off the floors and walls and zooming in. If we right-click on the bottom column, we can see that the length is now greater than 12 feet. The column has been lengthened to account for deformations. Rerunning the analysis with the new starting geometry, the vertical displacement at the top of the column is now only 0.08 inches. Far less than the 0.4 inches in the previous analysis. How do the displacements at each floor for this model with modified geometry compare to the previous analysis? Plotting the two analyses, we can see that the displacements for the modified geometry are considerably less. Thus, using the modified undeformed geometry command can help size members to minimize differential displacements. And on a final note, because this is a simple model, we did only one iteration of modifying the geometry, but for more complex models, several iterations may be required. In conclusion, vertical displacements can have a significant impact on the quality of construction in tall buildings, and thus buildings should be reviewed with construction sequencing and time effects to make sure that floors do not have excessive slope and that mechanical and non-structural items are not load-bearing. This concludes this ETABS tutorial on determining vertical displacements in tall buildings.